to get today goes. But mainly it's going to be a work day and then testing on Friday. And then beginning Monday, we'll get to do a deep dive into reviewing for our AP exam. So the problem that I wanted to do as a warm-up to kind of cover stuff from this week, but then also from before spring break, is from homework number 4. And again, some of you might have been ahead and already done this, but we're going to look at homework number 4 and question number 4. If you want to kind of switch over there, if you want to follow along. I want to do this one because it does hit some topics that I think are important to review, topics I know that will be on your tests, but then, just some good stuff to review. Things that we're going to be reviewing today. I wanted to review how to do a tangent line with differential equations, how we can use that tangent line to approximate the value on the graph. I wanted to do number 4 to review how to find the second derivative of a differential equation and determining whether the answer we found would be an under or over. And then, of course, probably the big idea from this unit is how we actually solve the differential equation. So kind of like 3 big skills that I want to make sure we review. So let's go ahead and read this problem. I'm going to kind of highlight the parts that I find important. So it says, at the beginning of 2010, a landfill had 14 tons of waste. That's kind of like an initial condition. It gives us the function. It tells us that this function dw dt, that is the differential equation for the amount of waste in the landfill. W is always increasing. That might be important. I'll go ahead and highlight it. And it does tell you that W is in tons and T is in years from the start of 2010. Key facts that I can kind of pull from that. If it helps you think about it, basically W is acting as the Y coordinate and T is acting as the X coordinate. And if T is measured in years from the start of 2010, then basically T is equal to 0 is going to be that year 2010. So let's go ahead and look at this question. And again, please feel free to interrupt me and ask questions as we're going over it. Some of this stuff, I hope you remember all of it, but some of it might be a reminder since we did have that week off in the middle of the unit. This first question is asking us to find the line tangent. So we need to do that first. Things we do already know, a tangent line, y minus y1 is equal to m times x minus x1, where we have to have a point and a slope. We're asked to find the tangent line when t is equal to 0. So your point is going to be at 0, comma, the y-coordinate at 0. Well, the y-coordinate at 0, that's where my initial condition can come into play. 0, comma, 1400. Well, what is the slope? We know in calculus that the slope is the derivative, and we know what the derivative is. dw dt is the derivative. And we want to find the derivative at that t is equal to 0. So we can plug that in, but we do need to be careful. So I have 1 over 25 w minus 300. I'm not going to plug in 0 there because that is the w. Well, what is the w when t is equal to 0? The w is that 1400. And then I can go ahead and just simplify that 1400 minus 300, and then divided by 25. So I see that my slope would be 44. And then from there, I can go ahead and just write my tangent line. Y minus the y-coordinate is equal to the slope times x minus the x-coordinate. That answer's fine, or some of you might simplify that. That answer is also the tangent line. So we've done that part. Now we need to do the approximation. So if you recall from before spring break, we don't know what w looks like. So it's like could be some crazy function. But if we know the tangent line at a point, then at least we can kind of use the tangent line to approximate the function as long as we're close to where that tangent line is. So if I want to approximate the amount of waste in the first 3 months, which they tell me is t is equal to 1/4, We basically know that w of 1/4 is approximately the tangent line, plugging in 1/4 for x, or t if that's the variable you used. Simplifying, 44 divided by 411, 1411 tons. So that would be the approximate amount of waste we found using the tangent line. Questions on that first problem? All right, let's move to the second one. I chose the second one because I think this is a skill that students often forget. I can promise you there's going to be one question related to it on your test on Friday. And that is finding the second derivative of a differential equation. I'm going to go ahead and rewrite that differential equation here. dw dt is 1 over 25 w minus 300. And it's asking us to find the second derivative. Things that we need to remember. Often when you find the second derivative of a differential equation, we have to use implicit differentiation. And it might have been a while since you've done this one, especially if you were probably good and finished homework 1 pretty early after it was assigned. Let's do a little time out and review implicit differentiation. I know those of you who didn't have me first semester, you didn't learn this at all until I showed it to you. Those of you who did have me, always good to review. So again, I'm just going to make up an example. Say this is my differential equation, and I want to find the second derivative. This is the derivative that dx in the bottom tells us we're doing it with respect to x. When I look at this problem, there's an x, so we're good to go. This is a y, which is not an x, so that's why we have to do the implicit differentiation. So looking at this one, what would be its derivative? The derivative of 2x would just be 2. Minus, we have the derivative of 3y squared, which is 6y. And here's where the implicit part comes into play. Times, we had a y, we wish it was an x. That is the second derivative. Often we want to write that second derivative in terms of just x and y. Well, what is dy dx? dy dx is this. So I can plug it in, leave it like that, or simplify. So I have 2 minus 12xy plus 18y cubed. And again, why we did that dy dx is because of this process called implicit differentiation, where we said, man, I took the derivative of y, but we were doing it with respect to x. So we had to multiply it by dy dx. Why did I review that? Looking back at this problem, we are taking the derivative with respect to t. But if you look right here, this is a w, which is clearly not a t. So we are going to have to do it implicitly. That 1 over 25 is a coefficient, so it can come straight across. What's the derivative of w? The derivative of w will be 1, but we had a w, I wish it was a t. There's the implicit. That minus 300 is going to go to 0. And then we just want to finish it out because we do want to put it in terms of w. So 1 over 25. What is dw dt? 1 over 25, w minus 300. Simplifying if you want, 1 over 625, w minus 300. And that would be the second derivative. So we've done the first part of that problem. I'm going to pause there. Any questions with finding that second derivative or with the implicit differentiation?
No.
All right, thanks, Mitchell. So looking at the second part, again, let's remind ourselves how we do it. Use the second derivative to determine whether your answer is an underestimate or an overestimate. Again, kind of going off to the side to remind us of stuff we know. We found a tangent line. That tangent line is going to be an underestimate if your graph is concave up, because it's going to be bending away from it in an upwards motion. That tangent line is going to be an overestimation if that curve is concave down. So that's why they asked us to find the second derivative. We need to basically figure out, hey, is this second derivative positive or is this second derivative negative? And we can figure out what it is. So I do see it's w minus 300. Well, we need to figure out, is that always going to be positive or negative? And we can use some clues from the problem. So it tells us the initial is that 1,400 tons, and that graph is always increasing. Well, if we're at 1,400 tons and the graph is always increasing, that is all going to be the smallest value of waste in it. It's always going to be increasing from there. So if W is always bigger than that 1,400, we know that the second derivative will always be greater than 0, because 1,400 minus 300 is positive. Since the graph is concave up, we know that this estimation we found in the first part is under the actual value. And again, you could have also plugged in 1,400 because that's close to 0, but that's kind of the better mathematically way to think about it, is since this graph is increasing, W is always bigger than 1,400, so that second derivative is always going to be bigger than 0. So then looking at this last one, here's the big one, solving a separable differential equation. If you don't get any other skills from this topic, you need to know how to solve a separable differential equation. Remember, the phrasing will tell you what you have to do. So particular solution, we are going to have to solve for C. This equal W of t, we are going to have to get W by itself. And of course, we have the initial condition. Only need one initial condition because they've already given us the differential equation. We didn't have to write it ourselves using the proportionality equations or anything. First step you always want to do, always separate your variables. We're treating W's like the Y's. So I'm going to put them on the left-hand side. I'm going to leave that 125 on the other side, and I'm going to move the dt along with it since we're treating that like the x's. Why do we separate our variables? So that we can take the integral of it. These w's, that's w minus 300 in the denominator, raised to the first power. So with the natural log of the absolute value of w minus 300. 1 over 25 is a number. Its antiderivative, 1 over 25t. And then please don't forget the plus c. I will say, if you drop that absolute value, that would be okay because of what we talked about earlier. You're not going to have a negative amount of waste in the landfill, so it doesn't really make sense to use the absolute value there. So if you dropped it, that would be fine. If you left it, that would be also fine. So now let's go ahead and plug in that initial condition. I have the natural log of 1,400 minus 300 is equal to 125 times 0 plus c. Easy one. C is equal to the natural log of 1,100. And then I can use that to write my equation. So I have the natural log of w minus 300 is equal to 1 over 25t plus the natural log of 1,100. Now, if this statement right here, the w equals w of t, was just not there, you could stop right there. Unfortunately, it does say equals w of t, so we do need to get the w by itself. Not difficult. How do I cancel out a natural log? We want to take the e of both sides, a single e on both sides with everything in the exponent. On this left-hand side, we just have w minus 300 left over. And on this right-hand side, we have e to the 1 over 25t plus the natural log of 1,100. Don't cancel out that second natural log, so we have that plus sign there. That would be some bad algebra. And then solving it for w, I have w, I'm going to write it as w of t, is equal to e to the 1 over 25t plus the natural log of 1100, and then outside the exponent plus 300. This answer on the AP exam, on my test, that answer is perfectly okay. If you were going to simplify it, you could. Again, I do want to say, if you have a correct answer and simplify it incorrectly, you're wrong. But if you leave it unsimplified and it's correct, then it's correct. So for many of you, it might be safer to leave it like this. But if you want to simplify it, when you're adding inside of an exponent, that's going to be split up as a product using properties of exponents. Now that that e is touching the natural log, it cancels. And a simplified version of this one would be that 1100 as a coefficient in front of the e, still having that plus 300 on the outside. So notice that that 1100 is multiplied, not added. That's a common mistake I see when simplifying. That's the better answer, but honestly, this unsimplified one would earn full credit. So in many ways, it's not worth the risk to try to simplify it. Did want to talk about how this would be graded on the AP exam. This last one was worth 5 points. I would grade it similar for your test. You got 1 point for separating your variables. You got 1 point for finding your antiderivatives. Here's an easy point. You got 1 point just for having plus c. You got 1 point for plugging in the initial condition. And then you got 1 point for having an equation in the form of WT. Also, though, on the AP exam, if you didn't separate your variables, so no separation, 0 out of the 5 points, nothing. If you have no plus c, the maximum you would get would be 2 out of 5, nothing after that point, no matter how correct or incorrect it ends up being. So again, if I can emphasize to you, if you're doing a problem like this, even on your test, the AP exam, if you can just do the easy part, separate and take the integral and making sure you slap down a plus c, you've earned most of those points. And earning most of the points on the AP exam is an easy 3, 4, or 5. So with that being said, any questions on that problem?
So when you said you would take off a point if it's not WT, does that mean that you have to write down WT, or could you just write down
No,
W?
as long as you had W by itself, it would be fine.
Okay.
So if you had stopped here, not earning full credit, if once you get W by itself, that's where you earn the full credit. But you wouldn't have to write it as WT. That is more just reminding you that like your final answer needs to be a function. So no like plus or minus or anything like that in the front of it. Any other questions on that one? All right, so I'm going to go ahead and stop the recording.